this video we're going to look at the first episode of our wave-particle duality. So we're going to talk about what that means, but specifically it's just talking about how we confirmed that light behaves both as a particle and a wave. So the science understanding for today's lesson is listed here. There's a fair bit of stuff there, but a lot of it is a fairly basic introduction. It's just sort of words and explaining things, and there's not a huge amount of actual calculations and formula involved. So to start off with, let's look at photons. In the double slit experiment that we've seen in the earlier module, we saw that light waves interfere and they form that pattern on the screen, and we get that interference pattern. When light interacts with matter, however, the wave theory of light doesn't explain what we see, and we'll cover that in a minute. So instead we find that the effects of this can actually be explained if we considered light as a particle. So we find that we end up with this situation where we've both confirmed that it's a wave using the double slit experiment, and then in the experiments that we're going to cover, we'll show that it actually acts as a particle as well. And so therefore we say that light is both a wave and a particle, and that's where this concept of wave-particle duality comes from. So with the photon, a light particle or whatever it is that we're talking about, it interacts with matter. And when it does that, it does so in such a way that it can't be described by wave motion. When we talked about interference and diffraction, we saw that these were properties of waves. It has to diffract through a slit or a space or something like that, and then you get your half integer lambda multiples of a wavelength, and that's where you get your destructive, and your m lambda, your integer multiples, give you constructive. However, there's other explanations that we need to then consider when we're talking about light. So if we look at this image here, if we used a very low intensity light source, as in like a very, very tiny pinprick with light shining through it, or a very, very dull light or something like that, we can see that an image is slowly forming as more and more pieces of this light hit the screen, and it slowly turns into an image. And we can actually observe this happening. The same effect can be done using a two-slit interference pattern over a very long time. So again, if we have a very small or very faint light source and we have some sort of a screen that we're monitoring, it almost looks like we're adding more and more paint to this canvas over time. It's not an instantaneous bright spot, which is kind of what we would expect when we have a wave. You would just expect this wave front of light to hit and suddenly we've got an image. But we actually see the image sort of developing, so to speak, over time on a screen. So these pixels or spots are actually photons. They're making up the images and the light that we see. And a photon is considered a discrete packet of energy. That's sort of the word they often use for it. Each photon has an energy of E equals hf, and it has a momentum given by P equals h over f. I'll break these down a little bit more in a second. But the h is Planck's constant, so this will be given to you on your formula sheet. You don't need to know this, just know that h is Planck's constant. F is the frequency of light in hertz, and lambda, as usual, is the wavelength in meters because we're using SI units. We can still use this V equals F lambda equation that we used in waves, or we could just replace the V for C because we're talking about light in this case, so it has to be moving at the speed of light c. So we just replace that and we get this C equals F lambda situation. We can use this equation to find the wavelength if we know the frequency, and vice versa. If we knew the wavelength and we didn't know the frequency, we didn't know what kind of actual light was being produced, we could then use this formula to calculate it. So this is the really interesting thing. When everything that we see in our life, images, our vision, all of that, it's actually made up of lots and lots of these photons. So you can almost consider it like pixels, or like the resolution is to do with how many pixels, so to speak, of photons that we see. So all of our vision is made up of these tiny, tiny photons hitting our eyes. It just happens to be that photons move at the speed of light, so we don't see that slowly developing image that I showed you in the earlier slide. We see an instantaneous image because our brain can't process faster than the speed of light, so we don't see a dot and then 3 dots and then 5 and then 50 and a million and suddenly we've got an image. We just see the image straight away. But this is actually what's happening. If we could slow down light, we would see images slowly developing on our eyes. The energy of a photon is given by this equation, the E equals hf that I mentioned before. F is the frequency of the radiation, so the light that's being given off, h is Planck's constant. So that's just a constant the whole time. You'll be given that. An important thing to note, if you're using a constant, such as Planck's constant, the universal gravitational constant, etc., you can consider that an exact number. So it does not affect your significant figures. So here it's been quoted to quite a few figures, but let's say in the formula sheet it said 6.62, and the rest of the values given in the question are more than that 2 sig figs, or 3 sig figs. You can keep using higher resolution sig figs just because this number is lower doesn't affect it. We consider this to be exact. We know exactly every single digit, or so we say. So bear that in mind, that a constant doesn't affect your sig figs. You use the actual values that are measured because they have an actual scientific uncertainty or experimental uncertainty in them. One thing to notice is that this constant is very small, 6.6 times 10 to the negative 34 joule seconds. So the energy of each photon for one photon is very, very small. This is not a significant amount of energy. But as we said, we have millions and millions and millions of these things all the time. Just a single image is made up of these. So each photon has a very small amount of energy. That's also going to translate to a very small amount of momentum per photon. So when we look at that photon energy and we want to convert it into something, we can see that from this formula here, which is just your V equals F lambda rearranged, the F equals C on lambda, the frequency is directly proportional to speed of light, inversely proportional to lambda. So the energy, if we're saying that C is basically related to its energy, then we've got this directly proportional relationship between energy and frequency, and inversely proportional to its wavelength. If we substitute C as the speed of light into the earlier equation, E equals HF, we end up with this guy. We end up with E equals HC on lambda, because we're talking about a photon, so it has the speed of light in there, and we get this. So this is the energy of a photon is given by Planck's constant, the speed of light, and its wavelength. In this question, I want you to use these formula that we've just talked about and have a go at solving some of these problems. So calculating the wavelength of photons rather than just the wavelength of a random EM light source. So you've got a minute. If you need a bit more time, as usual, just pause it and have a go. Okay, so looking at the first one, we're just using the basic E equals HF formula. We plug in 6.63 times 10 to the negative 34, that is Planck's constant, and we were given the frequency in the question. So we were just trying to find the energy, 2.84 times 10 to the negative 19 joules. Calculate the wavelength of the photons in the red light, then we just use our V equals F lambda formula. So we go back to the wave equation, we rearrange, we get lambda, we end up with 6.99 times 10 to the negative 7 meters for our wavelength. Momentum, we just use that momentum formula. So P is h on lambda. We now know h from our constant, our formula sheet, and lambda we found in part B. So we substitute them in, and we get 9.48 times 10 to the negative 28 sec newtons of momentum. So again, as I mentioned before, that is for one photon. So negative 28, 10 to the negative 28 sec newtons. So it has a very, very small amount of momentum. This is why in the earlier chapter when we looked at solar sails, and we said you've got those photons hitting the sail and bouncing back, we needed really, really big solar sails to try and catch a lot of photons. And even then, it's a very, very slow acceleration, because you look at how much momentum each photon is giving, you need basically 10 to the 28 before you've even got a significant amount of actual momentum force pushing on it, of sec-newtons. So then in photons in the X-ray part of the EM spectrum, they give you their energy in electron volts. So hopefully you remember how to convert electron volts if you need to. You just multiply or divide by the charge of an electron, the 1.6 times 10 to the negative 19. And they want you to determine the frequency. So we just use our formula here. They've converted it. So we've times by 1.6 times 10 to the negative 19 to get our joules. Then just plug that into the HF equals HF. Rearrange for F because we want frequency. And 2.31 times 10 to the 19 is your answer. Okay, let's look at momentum now in a little bit more detail. When light interacts with matter, it behaves like a particle. So that's the photon. When we're talking about light as a particle, we're talking about the photons. One of the fundamental principles of interaction of particles is conservation of momentum. So everything we've seen so far in motion and all that kind of stuff, momentum has to be conserved. An American scientist named Arthur Compton, who is the guy seen in the image above, experimentally found that when a photon hits an electron, they acted in such a way that the total momentum before and after was the same. So the momentum was conserved in this situation. The concept of momentum was developed for particles. And particles have mass and velocity, which is very important, because how do you calculate momentum when you've got P equals mv? In light case, how can a photon hit an electron? An electron definitely has mass, but a photon doesn't have mass. How do you do this kind of calculation? So what they found was that Einstein's theory of relativity, which links the E equals mc squared, was actually the solution to this problem. This implies that mass and energy are interconvertible or interchangeable. So you can have no mass but have energy, and it can behave in the same way as a particle with mass does. And this solves that sort of conundrum that we had with the photon. So you don't have to have mass to have energy, and they can act in the same way. So anything with energy can exert a force on an object regardless of whether it has mass or not, and anything with mass, which is our conventional understanding so far, can then obviously exert a force as well if it's moving. Given that matter from this example can be destroyed because we create energy. So in the nuclear topic from stage 1, this is one of the things we talked about, that in those fission reactions or fusion reactions, we have a change in mass. And that almost suggests that we're creating or destroying mass in this situation, but we're actually just converting it into energy, and that balances out this conservation and makes it happy. So even though the photons are constantly moving, given that we say they have no rest mass, so photons are massless, the energy can be equated and relativistic mass can be found. So looking at this, we've used the E equals HF so far, but we also know that E equals mc squared, so Einstein's theory. If we substitute them in together, we get this mc squared equals HF, rearrange or replace for the hc over lambda format, and therefore we can solve for m, and we call this the relativistic mass. So the relativistic mass of a photon is given by h, Planck's constant, divided by its wavelength times the speed of light. We can now use this to determine the momentum of a photon. If we say from our traditional non-relativistic scenarios that P equals mv, but that's also equal to h on lambda c times c, because v in this case is c and m we just found, so that's all we've done here. This is m, this is v. They cancel out and we get the momentum is h over lambda. So the fact that a photon has energy and technically no mass is actually enough to give it momentum. This is exactly how those solar sails work that I mentioned, despite the fact that the photons hitting it actually have no mass to push with. The energy is interchangeable, and the energy can behave like a moving object or a moving particle with mass does. So this is that derivation process of explaining why the momentum is Planck's constant divided by the wavelength. If we look at the EM spectrum, and we start with our visible and we work all the way up, we can see that the photon energy increases here. So as we go up in frequency, we get very, very high frequency, very small wavelength, the photon energy increases, therefore the photon momentum increases. So our gamma, cosmic rays, etc. can deliver a lot more momentum than our very small wavelength radio waves and things like that, because they have very little energy. And this is why high energy means high momentum, because it's interchangeable with mass. So high energy is equivalent to a particle of a very large mass. Low energy, equivalent to a particle of a very low mass. So it can't do a whole lot. So it all kind of makes sense. It all fits together now from early conventional understanding of the electromagnetic spectrum and the solar sail to now talking about it in terms of photon behavior and relativistic mass.
Girl, you can be my new thing.